river environments. The last of my 4 lectures, I talk about rivers and dams, and now a bit more focus on the environment. I have 4 subtopics here. One, the upland contamination, sediment management, because I know some managers here and give you some ideas. Reservoir turbidity and how to deal with turbidity currents. And then lastly, the aquatic habitat. In terms of contaminants, we talk about the Russell method that I like to use for the upland erosion losses. And I do like physically based models. I know we live in the era of AI, artificial intelligence, and there's a lot that can be done. But to me, physical modeling is very important because it provides a basis onto which we can tack on different additional processes. And yesterday I talked about the RKLSCP parameters, which is, those different layers that you can get in GIS for rainfall erosivity, soil erodibility, L and S, the 2 topographic factors, the cropping management from vegetation and conservation practice, for which then you can get in annual gross erosion maps in tons per year. You find areas that are more susceptible to erosion and others that are more stable. So this is a starting point to which we can add contamination. And the main point I want to show here is that we used to have no data. You'd collect the sample, send it to the lab, get information a week or 2 later. Nowadays, there are methods that are handheld. You can do gamma radiation surveys, X-rays, and so forth. And you can walk the field and get directly the information in situ. And you can see your map of your watershed on the right-hand side and see the dots for which you want to collect the data. The other big development has been that you can put some of those probes on drones, and then you can fly the field. If it's too highly contaminated for you and you don't like it for yourself or for your co-workers, then you can fly the area and collect the information directly in situ and come back home with a nice map of your survey of whichever parameter that you have, and you'll come up with a little map, in this case of arsenic, for instance, that is going to show you the hotspots of the contamination that you have on the ground. From this, the point I want to make in terms of technology is to link this with my presentation yesterday morning, where you can link this with the upland erosion mapping that we have. And you're going to say, I'll erode, let's say, 1 kilogram of this soil, on mean annual basis. But your contamination level is going to tell you that you have, let's say, 1 milligram per kilogram of arsenic, or maybe it's uranium, or maybe it's radium, or whichever contaminant. You say, well, I have 1 kilogram, so times 1 milligram per kilogram. So you expect to get 1 milligram of arsenic to move out, being eroded from those upland areas. And this is the technology we developed with Aaron Orekwa erosion that we got from the mapping I showed you yesterday, and at this site, and then multiply, kind of superpose a 7th layer there of contamination, and then we can get an erosion, upland erosion, for now, not the soil, but really for the contaminant per se. And then we can do the routing of those with the sediment delivery ratio that we talked about yesterday, since we're dealing typically with small watersheds, so a sediment delivery ratio is pretty high, and then we can get some erosion rates that are, like you see here, that may be over 2,000 or 3,000 tons of, that's a gross erosion rate, and you multiply by the contamination percentage, and you're going to get a concentration of contaminants that's going to be deposited into your detention pond. So the idea for this site is really to design, you can see in yellow in those 3 areas, with one here, little detention ponds that are designed specifically to trap the sediment and the contaminants into those areas. And you can see that you can calculate, you predict on the far right column how many milligrams per kilogram in the sediment deposits that you will have in your little detention pond. Let's say order of 12 milligrams per kilogram there. And the left-hand side is what you observe. You can go in the field and you can measure this, and you get some variability within the different areas, or within your detention ponds, and you get between 3 and 21, the average 10. So you compare this with your predicted from the Russell approach that I just described. So that is the kind of new technology that can be very helpful for upland erosion or upland contamination studies, and we have applied fairly successfully. My second point is the dynamic modeling. I talk about T-Rex, and yesterday I talked about two-dimensional runoff erosion. So the water and the sediment we did. I did not talk about the X. The X factor is really any contaminant that you can get. On the right-hand side, I showed Cal Gulch, and that's another sensitive area, so I have to be a little careful here. But I want to show that we can get, we did zinc, copper, and cadmium. We work with Will Clements, who is professor at CSU in fish and wildlife biology, on a paper that came out in ESNT. That was a super fun site, and we're in collaboration with Bill. And then we did the modeling, like I showed the floods yesterday in 3D with the water coming in and the long, detention of the flood wave on the floodplain at the downstream end. But we can do the same thing with those metals. This kind of thing I do not want to show and talk too much about, but we had AVIRIS surveys, which is airborne visual infrared spectrometry. So it is they fly aircrafts, over the site there, the Superfund site, and they detect the types of metals that are on the surface of the watershed. And from this, you're going to get acid mine drainage, and also a source of those metals. We're talking metals, zinc, copper, cadmium. And Will Clements had a little algorithm that he did, toxicity studies with fish and with macroinvertebrates at CSU. And he got a cumulative criteria units for acute and chronic toxicity for those invertebrates and also for the trouts and the aquatic habitat. So what the model can do, it's really, now we're looking at a big event, a large event, 100-year storm or something like that. And you're going to see initially in the top there, the distribution of contaminants, and mostly in all the upland areas. And as the water comes in, and as I showed yesterday, the water comes and enters the main channel, then drains downstream. Well, you're going to see the transport of those contaminants, the zinc, for instance, starting to go into the channel network. As the discharge increases, the concentration increases as well, and you start seeing the routing. You see now the concentration, high concentration, darker color is still here. And as you go a little later, then it goes out there and eventually comes out the door. So we can do this kind of modeling and superpose this with KMLs in 3D watershed units that get GIS videos and this sort of things. The other thing that can be done, and though we didn't do, but the model has the capabilities that if you have two mines, you have one mine that's, let's say, located in this area, and they will feed this tributary, and one mine that's located down here that feeds the other tributary. You are capable now to determine how much pollution is going to come from mine A as opposed to mine B. And this is a potential that can go to court and be very, very fancy. We have not tested this thing, but I tell you, this is where the technology is a bit more advanced than the applications. And I just want to let you know that those things are possible. The really number one world expert on this has been Mark Velou. Mark Velou has been the guy who's been spearheading their analysis and development of the code T-Rex. He had a lot of experience with the environmental side and the EPA. And we had all the hydrology, hydraulic, sedimentation. And when we coupled those two models, CAS2D said, with his environment model, then we got T-Rex. And Mark was involved also in studies that he did the nuclear material. That you remember the Fukushima Daiichi nuclear disaster in Japan. So Mark did some simulations and work at that site, and then got involved in pretty fancy modeling out there. My second topic is the sediment management. That's a project in Korea from over a period of 3 years. The mandate of President Lee Myung-bak, they decided to have a major river restoration program in South Korea. So they invested a huge amount of money to build 16 of those low-head dams on the river. The Nakdong, you see the location on the Nakdong River here, the Han River up north, the Yum River and Yongsan here. This is mostly a sandbed river. We talk about this. I showed here Pusan here, and there's some case a little earlier today. The Han River, the top one is Ipo, and I'll talk about this one today. The other one is the uppermost on the Nakdong is Sangju, that I will talk a little bit about. So over a short period of time, they wanted to, improve for flood control, have some restoration, to water supply also that tends to be low during the summer months. So they want to be able to store water and distribute this more effectively, and also for a little bit of environment. But when you mess up the river so much, the environmental aspect has been a bit on the side there, I must say. They excavated half a cubic kilometer of sediment. So we're talking about a kilometer long, a kilometer deep, and 500-meter high of sediment in those 4 rivers in a period of 3 years. They used this material. What the government did, they excavated this material and distribute this to all the cities involved. So the federal paid and gave all the material to city A, B, and C, and say, well, you can use this material and use it for construction. So like Rob explained a bit yesterday, some of the material, this was dredged from the riverbed and not from a dam deposit. But still, what he mentioned is very important, that there will be a scarcity of construction material. And this was one of the purpose of this project was to recover a lot of material. So Saint-Jouir, that's the one on top of the Nakdong River, the one that brings a lot of sand. You can see it's a nice sandbed river that is, a very nice, pristine area. And I showed you Saint-Jouir, also the area that is with the model. You remember with all the areas in the South Korea with T-Rex that we did quite a fair amount of modeling over the whole drainage basin. We're a little farther downstream here. And this is the weir, Saint-Jouir, after construction. You see a little powerhouse here, right? So micro turbines here. You see 2 major floodgates. Of course, you want to get the main floodgates on the outside of the bend and make sure that you don't get silting at the intake of your powerhouse, a problem that Professor Ettema really dealt with in great details in the past couple of days. Little flood control here, so extra weirs, and then you have a little fish passage that goes left and right here on the right bank of the river. So one of the issues for management has been that, well, they want to use this micro powerhouse to generate some electricity. It's not huge. It's about 3 megawatt, 2 units at 1.5. So it's not generating a huge amount of power, but still, say, let's use it. So, well, what do you want to generate hydropower with? Well, you need a good head and some flow. The flow is limited to the turbine, so that is fixed, but the head can vary a little bit. So the benefits from using this powerhouse has been increasing with the stage that you get upstream of the low head dam, as you can see. Well, now, if you keep the low head dam too high, then you get sediment coming down from upstream, and now you're going to store some sediment, and you're going to lose some storage capacity, and eventually you may have to dredge this all out. So you get pro, meaning hydropower, but the other one is going to be excavation that may be a cost to you down the road. So they tried to estimate the cost of dredging here. And based on, remember I talked about NREB a little earlier this afternoon here, and the dredge that I showed you earlier, then the estimate that the cost was about $6 per cubic meter. It's a bit expensive compared to dredging costs here. They used to be $1 a ton, but I think it's a bit more like $3 now, which is very expensive. So they excavate about 13 million cubic meter here. It costs them about $2 million a year. So that's over about, 20 some years. Like I mentioned earlier, some companies, I went there and tried to get them a proposal, say, hey, we can study this site and change the operation scheme of the gates and flush the sediment out and whatnot. No. So, instead of paying $2,000, $250,000, you'd rather pay $2 million a year. Then they will dredge that. That is all in their system. Say, hey, that's your problem. Deal with it, But this is interesting how some governmental agencies around the world operate. My point here is the hydraulic threshold. So on the left-hand side, you want to calculate the benefit cost ratio of running. That is the stage of that low head dam. If you keep it high, you can generate a lot more hydropower, so it's proportional to the head. So as you increase the head, then you generate greater revenue compared to the cost of your operations. If you keep it too low, all of a sudden you get some air entrainment, you get low efficiency of your turbine and so forth. So all of a sudden, it is not a good idea to operate at very low head in your dam. The other side here, what you see is going to be, actually, we define a threshold here. A threshold for BC is equal to 1. Say, hey, if the head is 40 3.5 meters, that's elevation above the sea level. If you're above this thing, it pays off to run. If you're below this, you should shut down the plant. It's not going to be very productive. So you get the hydraulic threshold. Now, the other one on the right-hand side, we're going to talk about the discharge threshold, which is the idea that, well, if you keep the gates high, then you get more sediment coming in. You're going to trap more sediment and you're going to dredge more sediment. So yes, you're going to make money from the operations of your micro power, but you're going to have more dredging costs. So the dredging costs in black will overrun the benefits that you get from the power production. Make sense? So, well, the idea is you get a threshold now in discharge. As you increase the discharge here, you get big floods, bring a lot of sediment, a lot of sedimentation, and now all of a sudden say, hey, wait a minute here, it's going to cost us more to dredge this material than the benefits we get from the hydro, which is essentially fixed. Make sense? So you get the discharge threshold, which is about, in this case, 620 cubic meters per second. It means what? It means if you get low flow, well, you're going to get much sediment coming into your reservoir. Don't worry about it. You just generate hydropower. But if you get a big flood and you bring in tons of sediment, then you should just open the gates, let the flood pass through, flush everything out, and you don't have to deal with this. So the discharge threshold is that if you get below 620, well, it's still a good idea to operate to get a hydro and get a little bit of sediments, no big deal. But if you get a high discharge, you get the flood, 620, open the gates, let the flood go. And Dr. Ettema yesterday talked about something very similar with the ice problem at the intake of one of his, forgot which one on the, I think the South Platte River, where he said, well, you know, if you get this condition, that condition, low flow and temperature and whatnot, you should just shut down the plant and just don't have diversions into your irrigation canal or, you know, your water reservoir and so forth. So it's not really a new concept, but it's something that is helpful. Now, my student, Wai-Young Kim, he was working with K-Water, so he did his PhD with us. And now we start getting into this project per se and try to expand beyond just hydropower and sediment here and sedimentation. But you start looking at the water supply. If the water level is too low in your river because you dredge so much, then you cannot operate your intake to, you know, diversion and so forth, the water supply to the city, X, Y, and Z. If the water level is a bit higher, now you can operate this no problem. So therefore, there's a cost of operating very low. So now you're going to define a storage or a water level that needs to be minimum in order to be able to have those diversions. Does it make sense? Yeah. So now you get a criteria that is based on the stage of your operation. For flood control, well, now it's a bit different in the sense that if the discharge is too high, you're going to flood your areas. And if it's too low, that's why you're okay. So now you get a discharge threshold, meaning that you don't want to be too high because now you're going to flood some areas. You see this coming? So we're going to define constraints in our system. Turbidity has not been the big issue. I mean, it's still pretty high, between 1 and 100 NTU, nephelometric turbidity units, and you get a high variability. So it's very hard to connect this to discharge and whatnot. So the water is always a little bit milky or kind of a bit of a hot chocolate color out there. And lastly, on this project, the $20 billion project, they built a bike path and parks and theaters and all kinds of things for the public. This one is more for recreation and campgrounds and so forth. So you can go biking from Seoul, the capital, the north, to Busan in the south. They built 450 kilometers of path there, and they wanted to bring the people closer to the water. And you could define here an estimate here of percentage of preference of flow width there actually as function of the stage there, meaning that if the water stage in the river is too low, well, there may be some odors coming from the site, and you see dead fish in the river and whatnot, and it's not very pleasant. And if it is a bit higher and it gets real high, and all people love that. They just love to be there by the river. It's just a nice elevation. You can get close there, go fishing, you go biking in nice weather, and if you get a flood, then your index starts to drop again because now you start flooding some parts of the bike path, and maybe it's not very pleasant to go biking along the river. So you get a peak somewhere, and the recreational value of your site there. So the idea for Y Young was to say, how can we combine this all together? So we developed, I'm not expert on this, but Daryl Fontaine, a colleague of mine at CSU, was, and he retired now, but Daryl was helping with the multi-criteria decision analysis, MCDA, in which we tried to combine the effects of water supply, flood control, stream ecology, riverside environment, turbidity, hydropower, and put this all together into how can we manage all of this. And we figured out that the main factor reduced to two parameters, meaning the stage at which you're going to operate, the water level, and the other one is the discharge. And certain times of the year, then you may have some restrictions as you want to get the irrigation, or you need water supply, or you want the biking maybe in July. Maybe people want to go biking in July, but by September, everybody is in school. So you define some constraints in terms of discharge, less testing for turbidity, and then maybe you want this less than this value, like the 620 we had for sedimentation. Maybe in May and in September, you want the water level to be above this for the irrigation purpose, but in October, we don't care about that. You know what I mean? For water supply, you'd be above certainly. So now you can define some scenarios in which we'll say, well, during this time period, we're going to operate under this condition, and maybe next month is going to be something else. So you define some preference and say, well, this time of the year, we really like the recreational part. We want to bike along the river for those 2 weeks where everybody's on vacation and so forth. And after that, you give it a low rating and whatnot. And maybe you want to generate hydropower maybe from September all the way up to April. And then in the summer, you leave this more for recreation or things like that. So you develop scenarios, and then you want to give them some value that of preference. What MCDA is going to do for you is going to give you a quantitative value for which scenario is preferable based on what you judge as being more valuable. So you get different alternatives here. And now the scenario number 5 is the one that would give you the best rating, whether it's based on money, whether it's based on dredging or whatever. So, but this is one kind of a conglomerate of all those values, of all those parameters. That was his dissertation. All right, so this is the Yipo Weir. We're going on the Han River now. You can see something similar to this. You have to give a lot of credit to the Koreans for designing things in 3 years. They have to start with nothing. They dredged, they designed, they tested, and they constructed. This looks like a bird with the eggs of the bird right there, Yipo Weir. And it has to go with an old tradition in South Korea of a poet who wrote something about the beauty of the river and was a kind of white egret or something. And so they tried to design, the engineers in collaboration with the artists, and design like of a bird and then giving birth with eggs and golden eggs and things like that, kind of fable. And they tried to incorporate this into their design. They all have similar features, hydropower here, the gates and control. Here you get a little bit of your fish way. They have a little bit of a theater. They have a little bit of parks here to play soccer and go in the summer, campgrounds that are going to be in this area, the bike path, and so forth. So that was the idea of the $20 billion stream restoration project. I got involved into this thing because in the upper right there, the gentleman there became Minister of River Restoration. I think it's the first time in the world that any government created a position of Ministry of River Restoration. And on the other side of me, that's Unji, that was a student. The minister, he got called into the Blue House, which is the equivalent of Congress here. And he said, well, we'll give you $20 billion, but you're responsible for the construction of all those 16 dams here. And we'll give you money, but you have only 3 years to get it done. Goodbye, that is your problem, right? So, those guys are under a tremendous pressure. And the Bureau is also one of those agencies, Corps of Engineers. They have big plans and they have to get things done quickly and whatnot. And many times they will call Professor X or Y and say, hey, you're the expert on this. I need your help. And we turn around and say, wow, well, I need a good, smart graduate student, someone who is really bright, great potential, is going to bring a lot of brain power to very complex problems. So the faculty are becoming like what David Varyu was saying yesterday. Well, a bit part of the problem in that we take people with little knowledge of problems and all of a sudden say, well, try to solve this thing. And you get your master's, you get your PhD education. And we're kind of the faculty are kind of the bridge between the young brains and then people who have to solve major problems of engineering problems and meet the challenges here. My third topic is about reservoir turbidity, and that's also in Korea because I work quite a bit in Korea and work with a lot of engineers at KICT and K-Water. By the way, the student I showed, the Unji, finished her degree. She's faculty and also working at KICT, Korean Institute of Construction Technology, and she's handling good budget for research and whatnot. Turbidity can be a problem. This is Ettema Dam. I showed the whole watershed that we modeled yesterday with Russell. So here in this case, you can see you get sediment in the reservoir. I mean, it's a big reservoir, right? So you see what's coming out is still sediment and the chocolate milk here. So you get a problem here, right? We have trap efficiency and can talk about this kind of thing, emergency spillway, Ettema Dam. So what do we do with this thing? What can we do? Well, K-Water, they get phone calls all the time, say, wow, we got our intake for the city of X downstream in Daegu and turbidity is way too high. We cannot operate in this. So, you need to do something with your reservoir. And the fishermen are just up in arms. We cannot go fishing. We cannot catch anything. Look at this colored water. You know how this goes, right? So maybe you get some feedback from the public every now and then. So you remember my little diagram here? That's the Andong Himha. We look at Imha here. This is Ettema Dam. And this is the watershed I showed you yesterday, right? So we talked a little bit about this. So that's where things connect a little bit. We have a very small input from Daeguk, but Banbyun and Yongjun bring most of the sediment out here. So now we're going to look at the reservoir per se and see what can be done there. What you do have, and that's typical of what you see in the United States in reservoir, you're going to get thermal stratification in the summer. You get the epilemion that is going to have higher temperature, 20-some degrees, so depending on where you are, California versus North Dakota. You may have different values, but typically order of 20 to 25 degrees Celsius in the summer. And that can be, in meters, that's about 10 meters, so that's 30 feet of depth there. Below width, you're going to get colder water down to 4 Celsius and maybe a little bit warmer, even in shallow reservoirs and whatnot. So you get a difference here in density of about, you go 1,000 at 4 Celsius down to 997.5, right? That's in kilogram per cubic meter. So it means what? I mean, my anchor point, get the rule of thumb, little number, my benchmark here. So what is it? It means that this is lighter water stays on the surface, but I could add sediment on top, right? And then if I add sediment, the density would go up. How far up can it go? Up to what concentration can I go that everything would have the same density, right? Well, it's 2.5 times 1,000 to bring this in milligram per liter. It means that you have grosso modo, here's an order of magnitude, 2,500 milligram per liter that you could have of fine sediment added to your clear water on top, and the water would still have a density less than the cold water underneath. Does it make sense? Yeah. So this is very important because it's the density difference that drives those density currents. We have a case where you have sediment entering in your river there into your reservoir. You get a plunge point till it comes down here. You will have thermal stratification to a certain level. If your concentration here is more or less than 2,500 milligram per liter, this is going to float and form a upper layer of very fine sediment in the interflow into a density current. So in other words, your density current is going to float on the surface of the cold water. Make sense? And if your concentration goes higher than, let's say, 2,500, that's my rule of thumb now, it is going to go down and you're going to get density current, sinking density current that's going to go as the underflow. The problem we have at this point is that the water intake, you design this and say, well, all the density current is going to go down here. We get the mud here, we get clear water, we extract clear water, and we release that, so there's no problem anywhere else in the river downstream. But because they place the water intake here, and you get the density current passing straight through it, then you just capture your density current and you just flush it downstream. That is exactly what's happening at this site. What can you do about it? Huh? So this is the question. That's what's coming out. Sang-Do did a PhD with me on this problem. So then, of course, they had a monitoring system. It's in general very difficult to measure the sediment concentration directly. So what you try to do, turbidity is easy to measure. And since we deal with fine sediment, then you can do a correlation curve between turbidity and concentration of sediment in milligram per liter. And then you measure turbidity, which is easy to measure. And then you kind of back calculate what the concentration in milligram per liter is going to be from that rating curve. Does it make sense? So what they do, they have floating stations loaded with turbidity meters that they float around the reservoir, and they're going to measure the turbidity everywhere as function of time. And what you see is going to be at different times here. After the typhoon, you get typhoons, like I mentioned earlier. At the elevation 135 or so, 140, you get the highest concentration, at 900 NTU, so very high values. And then later on, then the values will go down and so forth. And you may get still a little bit of clear water on top. And then, some that turbidity also floats all the way to the surface, get a bit of diffusion, like we talked about earlier. Now, I want to mention something with sedimentation here, because we're looking at fine sediment, right? So fine sediment between silts and clays. Silts, you get the law for settling of particles. For clay, at 4 micron, the time it takes to settle over 1 meter is about 1 day. That's another magnitude. That's another one of my benchmarks. 4 millimeter, you want to talk clay. 1 meter is going to take 1 day to come down, right? So if you have a reservoir that's from 150 to 110, let's say 40 meters, you're looking at a month for the sediment to settle out. So it means that if you have a density current like this with very fine particles like clay, then you're going to get that problem for a very long period of time. And you try to solve this thing, right? So the question, do you have silts or do you have clays? That's a 3D problem. It's pretty complex. We may have gotten away with 2D, but anyway, we did 3D. K epsilon, RNG, a RANS model. Fluent did very well with turbulence and so forth, so it's not the main problem. The main problem is that there was no settling in this. So Sang-Do then add a little bit of an algorithm for the settling of very fine particles according to Stokes' law. You give it the temperature and the size and so forth, and then we add this into the model. Let's go. So we feed it at the inlet there, and we let this go. That's a CAPI, one constant altitude plane. So, it took about two weeks to run, and we did runs at CSU. So you can see some little pockets higher here, right? But that thing diffuse and get a bit of advection. That's a density current that is propagating a little slowly. Of course, the model is going fairly fast. And at the end, you don't get much of a change, a little bit of diffusion that's going to go laterally all the way to the end there. Our intake, the dam is up there, and you can see where the intake, that is the elevation of the intake. Oh, we get it twice for the same price, so that's good. So the intake is up there, and then at that elevation of that simulation here. So you can see concentrations up to 1,000 milligram per liter, 500 is in the green, and 150 in the light blue and so forth. So you get a range of concentration through this system. The calculations are all 3D. The calculations are 3D. The visual representation for this video is only 2D at a constant altitude. Does it make sense? Yeah. So because the 3D representation is kind of very hard to show, and so we decided to just get one slice, horizontal slice at the level of the intake, and just leave it like that. They were measurements. So I normally tell the students to get the circles with the measurements and then the lines with the calculations, with the line calculations. In this case, they did the opposite. So you see the measurements are those points here right there, and then he did simulation from his model anyway. So, students don't listen to me much, but that's a different issue. But here we have the measurements, the observation. That's better, you see? The observation, that's the way I like it. And the line is the simulated from and you see the 3D over depth here. So you get the density current, you get the temperature profile that was given in to start with, and then we let the model run. And at the end, we see the new profile, which is the solid line that is going to be from the model at the end of the run. And then here you can see those different concentration of I think this is an NTU here, I don't see here, but NTU turbidity units here. So that's what was measured there, and that is what we measure. Calibration is still pretty good, and you can see you get an interflow. So that thing is really staying at certain elevation. And then below that, you get colder water, and the sediment will eventually get there, 1 meter a day, pretty much. And then that thing will settle down over a very long period of time. Show the interflow and the underflow regime. So once you have a model, that's a problem I faced a long time ago, is that you develop a model, okay, and you got some data, and you calibrate your model, and then say, I'm done. And in reality, it's kind of a stupid exercise in that, well, you had the data, you knew the answer, so why did you develop the model in the first place? So with students, of course, I cracked the whip for them to work all night and weekends. So I said, well, your model is good. Now let's use it. Let's try to learn something new from the model. What can the model teach us? So I told the student, and he was good enough to do those simulations. Let's change the concentration of those fine particles, right? So if we look at the ratio of concentration at the outflow to the concentration at the input, O is the output and I is the input. So initially we start at 1. So if I have a concentration of 500 milligram per liter, then we get interflow, right? So you look into this 3D model and say, where does it go? Well, it stays there. We don't have too many points because those runs were taking a lot of time. But we wanted to know at what value of concentration are we going to dip over and go to the underflow. So for this kind of case, which is typical, between 2 and 3,000. Now you see, I got my benchmark value in my pocket. Doesn't make sense. If it makes sense, yes, you see, you get your model to corroborate what you thought, right? Your benchmark value. If it does not, then you say, what's going on here? And now you can question and say, well, there's something different from what I had in mind. And then you improve your guessing ability as you go from one project to the next and so forth, right? So that's how I see engineering, and then you get a bit better and more knowledgeable. You expect this and you get that. Well, wait a minute. There's something else. I learned something, right? Here, same thing with the particle size. I said 1 meter a day, 4 micron or so around here. So now if I increase the particle size, if I have sand, that's going to go at the bottom. I will not get any density current. Yeah, so if it's very fine, then it's going to still be high. At what size is this going to start dropping out? The sediment will drop between 10 and 40 micron. So this is the range of particle sizes for which you'll get a mixed regime, and you need this kind of model, right? So if it is less than that, then it's going to be one regime, right? And if it's greater than 40 micron, don't worry about the density currents. They will not happen. The sediment will reach the bottom. Okay, my last one here, that is in collaboration with Reclamation, to which I'm very grateful to have been team leader for a 5-year project with the AAO, the Albuquerque area office, and looking at the Rio Grande Silver Minnow. Drew has been involved in this, so is Nathan Holsey, Nate Bradley have been reviewing. This is the Rio Grande. There's AgDeg information every 10-year. Field surveys there of cross sections. It's a wealth of information. Aerial imagery that I showed a little earlier since 1935. I would say 1918 was the first survey. I mean, the aerial survey that was not very high quality. So we have good quality data for a long period of time. We used ECRAS for this simulation. The river has been degrading in this reach. I just show one reach here. The upper reach we did with my students, Brianna Corsi, Chelsea Radubenko, and Tristan Anderson. You get degradation of about 10, 15 feet as a result of Cochiti Dam. So incision. The change over time, the river was wide and shallow, a lot of work on the river with those jetty jacks and levees, and try to channelize and prevent the river from impinging on the left bank and right bank levee all the time. The river adjusted very well. Tamara Masson was working here at USBR, and she developed a classification based on the Rio Grande, stage 1 all the way to 8, and to which drew with a lot of input from our reviewers. So we added a cross-section profile that goes wide and shallow all the way down to a single channel here, or some with oxbow lakes and so forth. So we kind of slightly modified this scheme. And the kind of things we're doing is really to tie in the fluvial geomorphology from the classification. We put in the real cross-section here of the river, and we show an aerial photography of the river. And we kind of go through this over time to see how the river changed. 62, 72, 92, 02, 2012. And you can see how the river used to be, stage 1, wide and shallow. And as you go over time, you get M5 now more narrow in size, well-defined channel within the floodplain. So this kind of work we're doing, and we used ECRAS. And 1D, essentially, we had to work on how many slices will I have, how many slices do you want to have within the channel versus the floodplain. And the idea is to get velocity and depth for the habitat for that minnow, Rio Grande silver minnow. So we get some model results at CRAS 1D, essentially flow depth at the given discharge, and we get the velocity and so forth. And, that looks pretty nice here. And those are the two parameters that are very important for the biologists. So we work with ACER and the University of New Mexico in Albuquerque. So Tom Turner, Steve Platania, who is one of the experts on the silver minnow, and they lead a team with Jake Mortensen. But essentially, they tell us for a different stage of development, the fish for larvae, juveniles, and adults, what is the range of flow depth and velocity where they find the fish. So they go in the river, they do seine holes and capture the fish and say, oh, we found them, what kind of velocity? Oh, yeah, about 1 foot per second or so, I don't know. And then, it was deep or deep or whatever. So they get the range where they catch things, where the minnow likes this kind of habitat. And for us, we're going to link this to our ECRAS simulation to find out where in the river do we find those conditions. So as an example here, on one reach of the river, you see those mid-channel bars and with vegetation or islands, you wish, and you will see based on velocity and depth, zones that are favorable. The crosshatch is really good for juveniles and adults. The light blue only is primarily adults. And the light green, which turns out to be critical for their survival, just in some remote locations, some of the bank line, the back channels and whatnot. And this turns out to be one of the key criteria or areas for collaboration. The biologists eventually help reclamation, develop some methodology to really enhance their habitat. Over time, we can do a lot of simulations here of the habitat that you get at different flow rates, 500 CFS, 1,000, 2, 3, 4, 5, all the way up to 10,000, which will not happen probably in the near future. We'll be lucky to get to a couple thousand here coming out from Cochiti. So we get the habitat index there for those discharges at different times. So before Cochiti Dam, meaning here, the purple and blue, you could see that the river was wide and shallow, and this was very good habitat for the silvery minnow. Since Cochiti, 92 and 212, now for a wide range, unless you have very low discharge in the river, which it's not necessarily the best here, but if you get a flood or something, it's not really favorable. You can have a very high discharge, but the habitat is not very, very good. Because the channel in size, the river has been narrowing, and the bank line is a little higher than before. So you need a higher discharge for the biddos to go onto the floodplain and lay their eggs that float, and then to let them hatch and develop, right? So this is the kind of analysis we do for reclamation. Chelsea did a little comparison between the 1D and 2D habitat. We took SRH 2D, which I think Victor and Young know very well. And the aircraft, it's a 1D, so we called it pseudo 2D because we kind of get the output from aircraft and dump it on the LiDAR in GIS and whatnot, and we get a 2D representation of the velocity and the depth. So we can do then comparisons at the given discharge between the velocity from aircraft, which is kind of standard code, and the SRH. You see slight differences, that is going to be, but they are not very significant, other than saying that you have some mid-channel bars or not. And then if you look at the flow depth, you're going to get fairly comparable results. We can compare, let's say, the aircraft 1D, that's what Chelsea did, and with the 2D, and more or less you see good habitat there on the other side of the river here, and between those mid-channel bars here in this area. On the other side, well, that's the outflow of the Mafka there. The little differences maybe in this area here and whatnot. So you can argue whether you gain or lose. The 1D, 2D, of course, is a bit better, but it's more trouble, right? So you need to feed it more data and work with that. So that leads me to near the end of my whole talk. Contaminant mapping and the problem source areas. Hydraulic thresholds and MCDA, the multi-criteria decision analysis, can be helpful for management of rivers with sediment. Turbidity problems, we can model this 3D. I believe you have the in-house capabilities here as well. This is kind of nice and 3D modeling effort. And the mapping of habitat, the TIMS and the quads, and like I show, comparison the fluvial geomorphology, cross-section, and then plant form geometry. I have to thank a lot of people. Then here, that is the last book I've written for undergrads in my class. Thank a lot of people. Aaron, Wai Young Sangdo, many Koreans here who helped me. The team at CSU working for USBR, Jake and Acer, the 3 reviewers with us, Ari also. And I'm sure I forgot many people, but I apologize for it's not intentional. Try to help, showcase everybody's work. I want to say a word about CSU. It's been my, not alma mater, but it's been really my employer for the past 40 years or so. I came here in '83. So I have enjoyed learning, and there's young people here, some people working 5 months for reclamation. Just keep learning, keep at it. Once you're mid-career, you may want to share discoveries and participate in writing papers, going to conferences, give talks, and so forth. And for the senior people, then, serve with purpose. I've been editor of the Journal of Hydraulic Engineering of ASCE and spending 30 hours a week to reviewing papers. Dr. Rob Ettema did the same thing too. In fact, he was my predecessor with ASCE. Rob has been involved as vice president of IHR, the International Association for Hydraulic Research. A lot of commitment to help the professional societies and so forth. So I want to say the commercial time here about CSU that we have been in business for a long time, 1902. Then we had people coming out from the American-Spanish War with those war caps all there, and then the idea of getting cross-section surveys there is not really new, even if we have the egg-dig lines here and whatnot. You can see students with white shirts and clips and whatnot, so it's always nice to see people with class at CSU. And today we recruit very talented students, and you can see people who love the outdoors, love the environment, love rivers and sedimentation. We get them into rigorous training at CSU. And some of you may remember the hardship of solving homeworks and whatnot due tomorrow. And I've not changed much over the years. But, sedimentation and river mechanics, I've been the classes I've been teaching for every other year for 40 years. So I've done this often. And it's the size of the smile on the figure's face that tells us when they're ready to graduate. As you can see, Drew may recognize Forrest J. This is my very last slide, maybe the most important. As professor, you work with a lot of people with all different gender, religious belief and creed, and continents and whatnot, so all over the world. And we work on problems in America, in Asia, in Europe, wherever. I cannot talk about everybody. This is my family. Could have told more about Patrick O'Brien and his work with the Corps in San Francisco district and the impact of sea level rise on the infrastructure. Right there, Mark Velu, who is at HDR, the expert, could have talked about Oi from Thailand, who did some CFD modeling on step spillways. I talk a bit about Sengdo. I could have talked about Shazwani, who is from Malaysia and work on the precipitation under monsoon, and James Hallgren with his video that you saw. John England, of course. I could have talked about his simulation of TRX for all the upper Arkansas River, all the way down to Pueblo Dam and whatnot. I talked a bit about Shukran in Afghanistan, Sima Shah, and so forth. There are so many, Unji that you saw, and Patrick Dologoy, who from Congo, and the problem that they had with slash and burn practices over there, and all the turbidity problems that they get at Kinshasa, having been forced to shut down the water treatment plants for 2 weeks or longer. No water for the city because they're burning all the savanna, and then all the ashes coming down the river, and turbidity is too high to operate, and so forth. Those problems around the world are very similar. And then we realize that we're in a small family of engineers, geoscientists, geologists, and computer scientists, and we're working together to solve those problems. And that's my family. It's time for me to retire.